This evening now to Professor Sir Colin Humphreys, who is going to take us on his research which has gone, I think, from traffic lights all the way to augmented reality glasses. Is this right, Colin?
Yeah, that's correct, yes.
Fantastic. Take it away.
Right, thank you. Fine, well, thank you very much for inviting me here. And that's just a wonderful talk we just had from Jenny. So Jenny, thank you very much. Really enjoyed that talk, and it's hard to follow that. And it's a great pleasure to be here. So to start with, thank you to the people at CSAR who make these talks happen. So thank you very much for that, not just for my talk, but all the wonderful talks that CSAR presents. And I'd also like to start by thanking the people who funded this research initially. So EPSRC have given really long-term funding of gallium nitride research, and they've given the initial funding of graphene research. And then Innovate UK have given us some more recent funding of the graphene research. But without these funding sources, this research really wouldn't have happened that I'm about to describe this evening. So it's really important. I'd like to thank them for their funding of this activity. So what are the most recent materials innovations? Well, one way of answering that question is to say, what materials have won Nobel Prizes most recently? And there are two of them. One was an award in 2010 to two Manchester University scientists, Gallium and Novoselov, and the citation was for groundbreaking experiments regarding the two-dimensional material graphene. And the other award was in 2014 to Akasaki, Amano, and Nakamura, three Japanese scientists, for the invention of efficient blue LEDs based on GaN, which has enabled bright and energy-saving white light sources. And so, arguably, these are the two most important new materials since silicon. I've been very fortunate to be involved in research on both of them, really building upon what these Nobel Prize winners did initially. So in this talk, I'd like to go from some basic science right through to exploitation. And the two journeys are rather different. So the gallium nitride exploitation has taken quite a long time, which is usual in science. And the graphene exploitation has been much more rapid from research that we've done. And this exploitation, of course, is really important because, as Jenna was saying, you can get huge benefits from society only if you exploit your research. So in this case, you can save energy, create jobs, save lives, and improve our health. The content of the talk, I'm going to start by talking about GaN on silicon LEDs. And this is really past exploitation, so looking backwards, and then move on to graphene and a quick introduction to graphene. So this is present and future exploitations, the high expectations of graphene that everyone had based on the brilliant basic science done on small flakes of graphene, then the hurdles to industrial applications, then the new graphene solution my group came up with, and then our first graphene product, which is a magnetic hall sensor, and then finally briefly talk about a graphene organic light emitting diode. And I'd like to thank the collaborators in GaN. So you may have noticed at the first slide, I have two addresses. One is Queen Mary, University of London, the other is University of Cambridge. And so I directed a GaN group in the materials department in Cambridge. And my contract wasn't renewed because of my age, because of Cambridge retirement policy. And Rachel Oliver now directs that activity very successfully. So Rachel Oliver is the person to go to in Cambridge if you want to talk about GaN. And then for the GaN on silicon research I'm going to talk about, I'd like to thank particularly Menno Kappers, Dan Denjou, and Clifford McAleese, and also Lewis Liu, and many more people who are actually involved in the group on this particular research activity. So if you go back to 2002, which is a long time ago, GaN LEDs were very expensive. And it's hard to believe this now, but a 60-watt replacement GaN LED bulb in 2002 cost about £50. A few people in England had them. So for example, the wonderful Prince Philip had some in Buckingham Palace. He was one of the first adopters in the UK of GaN LEDs. But most people just couldn't afford to put these in their houses. And they were expensive because they were grown on 2-inch diameter sapphire or silicon carbide wafers. And so I had this vision to try and reduce the costs and to grow on 6-inch diameter silicon wafers. And I had a research student, Matt Charles, who in 2002, his PhD project was to grow and characterize 3 nitrides on silicon. And in 2003, I got a 3-month exploratory grant from EPSRC to grow gallium nitride on silicon. So I got £53,000 for this. And Matt Charles achieved GaN on silicon LEDs, 2-inch silicon and 6-inch silicon wafers at the end of his thesis. So he achieved them, they gave out light, but they were not very efficient at that stage. So a lot more work had to be done in getting them more efficient. And this is the basic science part of the talk. So there are 3 significant challenges in growing gallium nitride on silicon. And the first one is there's a very large lattice mismatch between gallium nitride atoms and silicon atoms. It's 17%. And this generates a high dislocation density of greater than 10 to the 10 dislocations per square centimeter. The second problem is an extremely large thermal expansion mismatch between gallium nitride and silicon. It's over 50%. And what happens is you're growing gallium nitride on the silicon at about 1,000 degrees centigrade. And when you cool down, this thermal expansion mismatch is really important. And the gallium nitride is in tension, and so it cracks when you grow it, when you cool down. And the wafer also bows. And the third problem is you can't, in fact, grow gallium nitride directly on silicon because a gallium silicon eutectic forms, and that also etches away at the silicon wafer. So those are the 3 basic science challenges we had to solve to grow gallium nitride on 6-inch silicon wafers. So how did we overcome the problem of this melt back etching and the formation of a gallium silicon alloy? So what we did was to introduce a different material, aluminium nitride, which you can grow on silicon, and that formed an intermediate layer, a nucleation layer on the silicon. And the quality of that layer was really important for the final LED quality. You had to optimize it. And the quality of the aluminium nitride on silicon interface largely determines the quality of the nucleation layer and then of the LED. And what we found when we did an atomic resolution electron microscope, so here, this is aluminium nitride at the top, silicon at the bottom. We're growing the aluminium nitride on the silicon. This is a cross-sectional electron micrograph. The double dots you can see in the silicon, each dot is a column of silicon atoms. And so this is really high resolution microscopy. We're seeing the individual atoms in the material. And that's a 2 nanometer scale mark at the bottom. And really unexpectedly, when we put this in electron microscope, we saw this amorphous layer, which turned out to be silicon nitride, between the aluminium nitride and the silicon. And optimizing that amorphous layer was really important. In fact, if you lower the growth temperature, you get an abrupt interface. So this amorphous layer is due to interdiffusion of atoms across the boundary, across the interface, when you're growing at this very high temperature. So optimizing the growth conditions was really important for the quality of the aluminium nitride and the quality of the LEDs. So that's one problem that had to be solved. And then the next problem to solve is this problem of cracking because of this 54% difference in thermal expansion coefficient between gallium nitride and silicon. And the LEDs which were being grown at the time on sapphire and silicon carbide, they in fact, the differential thermal expansion coefficient works the other way. So gallium nitride is in compression on those substrates when you cool from the melt. But when you cool from the melt on the silicon, the gallium nitride is in tension, and so it cracks. And so what we did, we introduced deliberately compressive stress layers to compensate the tensile stress on cooling. And this was really quite sophisticated stress engineering at the atomic level in these materials. We formed 4 graded layers of aluminium gallium nitride. And the next slide shows schematically what's being done. So on the left-hand side of this diagram, the gray portion at the bottom is a silicon wafer. Then we grow aluminium nitride on top of that. And then we deliberately grow aluminium gallium nitride on top of that. And the unit cell, that's the atom spacing in aluminium gallium nitride, is greater than on silicon nitride. And so when you grow aluminium gallium nitride epitaxially on the when you grow aluminium gallium nitride epitaxially on the aluminium nitride wafer underneath, then you get then the aluminium nitride acts as a template, and so the aluminium gallium nitride is under compression, and you deliberately introduce the compression layers, which counters the tensile stress when you cool down, which would happen otherwise, and so you don't get the cracking. And then the third problem is to try and overcome this high dislocation density, because it reduces the efficiency of the LEDs. And so this is a very clever method, which if anyone talked to you about it, you would think you wouldn't believe it, but it really works. What you do is you introduce a silicon nitride mask. So this is a schematic of what is done. So the bottom of this diagram is gallium nitride with this very high dislocation density coming threading up through the material. And then the red mask is the silicon nitride interlayer. And this is a sub-monolayer thickness interlayer. So the red portions are actually just one monolayer thick, and the holes are natural pores in the structure because it's sub-monolayer thick on average. And what happens is the dislocations which hit this red bit of the mask, they are stopped from going through. On the other hand, so that reduces the dislocation density a lot. But on the other hand, dislocations still go through these random holes, and we can reduce that dislocation density further, because when we're growing the bottom layer, the bottom layers of gallium nitride, we do layer by layer growth. When we grow the gallium nitride on top of the silicon nitride, we change the growth conditions and we do island growth. And dislocations which come up through the holes, they may hit a side facet of one of these islands and go right, as it were, and another dislocation coming up through an adjacent hole may hit another side facet and go left, as it were, and these two dislocations can meet and annihilate, or they disappear then, or the two dislocations can be one dislocation, and that reduces the dislocation density. And you might think this is an incredibly rare event, but actually it's quite a common event. And we get 2 orders of magnitude reduction of dislocation density. And you can see this visually on this slide. So if you look at the left-hand slide, the bottom portion shows this very high density of vertical dislocations coming up. And then where it says first, that's the first interlayer we put in of sub-monolayer silicon nitride, and the dislocation density is drastically reduced. Then if we wish, we can put in a second layer and a third layer and a fourth layer. And in this sample, the dislocation density is reduced by 2 orders of magnitude. And you can also reduce the dislocation density in another way by introducing a silicon nitride interlayer. But we choose to do that, you have to take the specimen out of the growth reactor. And that costs money if you're trying to reduce costs. And so on the left-hand side, that's all done in the growth reactor without taking the specimen out. And so by that means, we've reduced the dislocation density by 2 orders of magnitude. And this enabled us then to grow gallium nitride LEDs on a 6-inch silicon wafer. And this photograph is an image of the first processed 6-inch gallium nitride LEDs, and it's processed by industry called RFMD, and that was done in 2009, and that was the first time in the world it was done. And in fact, the pattern you see on this wafer are test structures of LEDs of different sizes. And then the top right-hand side is a magnified image of part of this wafer, and then the bottom right, we're just passing a tiny current through one of these LEDs, and it's brightly shining. And in fact, it's emitting blue light, but it's so intense, it's saturating the detector, and so it looks like white light. So this was a great success story. As I say, it was all being funded by EPSRC. And then, so that was done in 2009, and we set up 2 companies to exploit this research in 2010 and 2011. And we knew we couldn't go much further ourselves, because to go further ourselves, we would have had to purchase a 6-inch processing line, a 6-inch silicon processing line, which are enormously expensive. And so at that stage, we looked to exploit the research in a British company. We actually put our results on the web, and before we could get a business plan, we were approached by companies in America, Japan, China, and the UK. And we thought, you know, the EPSRC is funding us, let's go with a British company. So we went with this British company, Plessey, and they acquired the companies in 2012. And I hired 3 of my postdocs to transfer the technology. And everyone said it will take typically 2 years to transfer technology from a lab in a university to a company. And in fact, it didn't take 2 years, it took 8 weeks. And Plessey were manufacturing these gallium nitride LEDs on 6-inch silicon wafers at their factory in Plymouth, UK. And this was the first manufacture of GaN LEDs in the UK. And Plessey sold 2 million LEDs in 2014. So they actually started selling in 2013 and then sold 2 million in 2014. So it got off the ground really rapidly and very rapid exploitation. After these years of research, starting in 2002, this final step happened really quite rapidly. And they were the first commercially available GaN LEDs on 6-inch silicon in the world. And Plessey now are focusing their attention on making GaN on silicon micro LEDs. And again, they're based on the Cambridge GaN on silicon technology. And these micro LEDs are so good that Plessey have chosen, sorry, they're so good that Facebook in 2020, just last year, chose Plessey as their partner to make micro LEDs for augmented reality. And why micro LEDs are so important is they're very, very bright. They're much brighter than normal LEDs. And in fact, you can see them in bright sunlight. So, you know, if you have a sports watch or a mobile phone and you look at the screen of the sports watch in sunlight, or you look at the screen of a mobile phone in sunlight, you can't see it. These are so bright, you'll see the screen even if the sun is shining directly on them. And they also remarkably consume very little energy. So that is really, you know, a very nice exploitation story. If we look at the energy savings from gallium nitride, then if we look at the LED lighting, the energy savings are so great that you save 15% of all electricity generated. So the actual numbers are lighting used to what's the right word? It used to consume 20% of all electricity generated from our power stations. And with LEDs, it consumes only 5%, not 20%. So it saves 15% of electricity from our power stations. And if that electricity is being generated from fossil fuels, then it will save 15% of carbon emissions from power stations. So really significant. And LED traffic lights, you know, part of the same. They used to be normal light bulbs, now they're LEDs. And so throughout the world, people are turning to LED lighting. It's a dominant form of lighting in the world. And then I haven't had time to talk about silicon-based power electronics, but in fact, if we can have gallium nitride electronics replacing silicon, that will save another 10% of electricity. So remarkably, this one material, gallium nitride, has the potential to save 25% of global electricity, which is really a most remarkable saving. And just before we started, someone told me they heard a talk of Dave King recently. I think John Cook told me this. And he had said that this is one of the great success stories of energy saving was gallium nitride lighting. So let me now move on to graphene, where the actual academic work happened very rapidly. So these are the collaborators I'd like to thank for the work on graphene. Simon Thomas and Ivor Guinea were both postdocs in my group in material science in Cambridge. They were both, in fact, postdocs working on gallium nitride. They then got recruited by Paragraf and moved to Paragraf. In fact, they then formed, Simon, Ivor, and myself founded Paragraf, and Simon and Ivor then went to work in Paragraf. Another collaborator on the devices I'll talk about is Hugh Glass, who we recruited from elsewhere to Paragraf. Eli Galanis, we recruited from QMUL to Paragraf. Yiwei Sun, Zichao Weng are 2 postdocs I have at Queen Mary, and David Dunson's a professor at Queen Mary. So this is the main team which has been working on graphene. Graphene, as we said, is a Nobel Prize winning material. Graphene is a 2-dimensional network of carbon atoms. It's sometimes called carbon chicken wire for the reason I'll show in the next slide. And graphene is the first material in which all the atoms are in a single plane. So it's, you know, a unique material, the first material in which this is the case. This is why graphene is sometimes called chicken wire, because the left-hand picture here is a representation of what graphene looks like, with carbon atoms at the intersection of these bonds. And if you stack up graphene layers, you get graphite on the right-hand side. And graphite is the lead in your pencil that you write with. And graphite has these stacks of graphene layers. They're weakly bonded to each other. It's called van der Waals bonding, and they rub off easily. So when you write with a pencil, you're rubbing off layers of graphene onto the paper that you write on, or you can also use graphite as a lubricant. Why is it called lead in pencil? Well, I only realized this recently. The reason is that graphite has been used for writing since very early times. In fact, it's clearly used in 4 BC in a drawing, but it's used for writing before that. And people thought graphite looked like lead. They're both very dark colors. And they thought in the early days they're just different forms of lead. And so that's why it's called the lead in your pencil, because graphite was also called lead. Okay, let's now move on. How do you obtain graphene from graphite? Graphite is a mineral which you can dig up. There's a big mine of graphite in Cumbria in England, in one of the Borrowdale, I think, a mine of graphite. And graphite was isolated from graphene was isolated from graphite in 2004 in Manchester, for which they got the Nobel Prizes. And what was done by the two scientists there, Gaiman and Novoselov, they used sticky tape on a block of graphite, and they had a block of graphite, put tape on each side and pulled it apart, and they put another piece of tape on and pulled it apart, and they kept on peeling off layer after layer after layer of graphite until they got down to a single layer of graphite, and that was graphene. And in a sense, they got the Nobel Prize for sticky tape. But that would be really unfair, because what they then did, they did these experiments of graphene, which showed it had remarkable properties. And these experiments were really difficult because a single layer of graphene is transparent, right? It's 97% transparent to light. And so think of doing experiments on a flake of graphene just several millimeters across, which you can't see. And they did a whole range of experiments. And later, other people did some brilliant experiments. So Andrea Ferrari in Cambridge, for example, had a big group and did a lot of the really basic work on graphene. And they demonstrated graphene flakes had remarkable properties, which I'll talk about in the next slide. Graphene flakes have been exploited, and also you can take graphite and powder it up. And they've been exploited, and they're being added to car tires, to paint, to concrete, tennis rackets. It's meant to improve your tennis. Running shoes makes them last longer, etc. And so they're widely used now in these rather low-tech applications, but they're important applications. But if we're looking for high-tech applications, for electronic and optical devices like transistors or sensors, then you need large area graphene. You can't take a graphene flake and make a transistor. You can't manufacture a transistor with a graphene flake. You can just make it in a laboratory. And these are some of the properties that were found on these exfoliated, using sticky tape, graphene flakes. Very high electrical conductivity, said to be 1,000 times better than copper. And of course, that promises high-speed electronics. Because it's got high conductivity, it therefore has low resistivity. In fact, it's the lowest known, and that promises very low power consumption of devices. It's highly flexible, you can bend it easily, promises flexible electronics. Very high thermal conductivity, promises good device performance. A number of devices are limited by the heat they generate, so this promises to help to overcome that problem. And then very transparent, so it promises transparent conductors to replace an existing transparent conductor called indium tin oxide, ITO, which I'll talk about right at the end of this talk. And what's remarkable is all of these world-leading properties are in a single material called graphene. And that's why this amazing material is unique in the world. And it was called the wonder material, and newspapers took it up, and it was talked about in Parliament and so on. So graphene is the wonder material, more conductive than copper, more transparent than ITO. And for this reason, all labs around the world and industrial companies, they invested huge amounts of money. So Intel have invested 750 million US dollars in graphene research. IBM, 3 billion US dollars. Samsung, 2.2 billion US dollars, because they saw if they could actually take these properties of graphene flakes and scale up the graphene flakes to a larger area, then they might make really very fast computers and really very sensitive sensors. And so they put all this huge investment in. And the problem is, where are all these wonder predicted electronic products? And in fact, these major companies now have really wound down or stopped their research into graphene. And this is another example. The left-hand side here is a report for the World Economic Forum, and it says graphene could soon make your computer 1,000 times faster. And of course, we don't have graphene computers. And on the right-hand side, it's from Financial Times. Graphene filters change the economics of filtering water. And as far as I'm aware, this hasn't happened. Graphene filters are not changing the economics of water filtration. Then in the middle, Bosch finds graphene magnetic sensor 100 times more sensitive than silicon. And that was based on making a sensor by hand from tiny flakes of graphene. So these remarkable results, which you can get at the laboratory level using tiny flakes of graphene, you can't manufacture that way. So the challenge is to scale up to commercial scale graphene from tiny flakes to larger area graphene. So what IBM did, they did assemble a graphene transistor themselves. They assembled by hand. Very difficult because you can't see the graphene, it's transparent, and they found this was 10 times faster than a silicon transistor. And Samsung found that you could have flexible contacts from graphene. And Bosch made a graphene Hall effect sensor, which they said was 100 times more sensitive than silicon, but that was assembled by hand, and you can't manufacture like that. And the next slide shows the press release which Bosch issued when they made this sensor. And this is what they said. It was a press release in 2015. It said Bosch creates graphic sensor 100 times as sensitive as silicon, but unlikely to compete for 5 to 10 years due to the current lack of large-scale, wafer-based and transfer-free synthesis techniques. So what they were saying was, we've made this wonderful sensor, but we can't manufacture it because there's no large-scale, wafer-based, transfer-free silicon, graphene, which is available. And large area graphene was then available and is still available using a technique called CVD, that's chemical vapor deposition. But what's done in that technique is the graphene is made by depositing gases like methane on copper, and the copper is used as a catalyst to decompose the gases and deposit carbon. And so the carbon then, which forms graphene, has copper as an impurity in it. And then if you want to use that graphene, you have to transfer it from copper to a more useful substrate, and you get impurities from that as well. So it's really difficult to use this for manufacturing electronic devices. So I had 2 senior postdocs in material science at Cambridge, and they solved this key problem of making high quality large area graphene. And they used metal organic chemical vapor deposition, MOCVD. That was a technique that my group was using to grow gallium nitride. So we had a lot of expertise in that. And Simon Thomas and Ivor Guinea had particular expertise in this technique. And other people may have tried this, but they weren't successful, so no one really knows about it. And this was the first successful use of MOCVD, and it was patented in 2015. And what's important about this technique is no metal is used as a catalyst. There's no metallic contamination. There's no transfer process because you grow directly on a substrate. And it's really promising for next generation transistors, biosensors, energy generation, and so on. And so the 3 of us, Simon, Ivor, and myself, set up a company to exploit this research. We called it Paragraf. We had venture capital funding for this, and we've raised what's called seed funding in October 2017. moved into premises in 2018, and we already have over 60 employees. So it's expanded really rapidly. And this shows you the Paragraf where we are. It's north of Cambridge in a village called Somersham. And a farmer was very innovative. He decided to erect these sheds on his farmland, large sheds or barns, if you like, large barns. And he said to people, and he called it the science park. Sorry, let's go back. Called it the science park. Called it West Newlands Science Park. West Newlands Industrial Park, and he said to people, come and use my industrial park. And we went there, and the cost of renting that accommodation is 10 times less than renting accommodation on the Cambridge Science Park. The Cambridge Science Park was a wonderful, absolutely wonderful place, but a bit expensive, so because it's so much in demand. And so we moved into one of these barns, and it really was an empty barn. There was no water, no electricity. So we had to bring in electricity from a substation. We had to bring in water. We found that the roof actually leaked. It was February 2018, which was quite cold. And when it snowed, the snow came in from the roof. That was, I think, the first day we went in there. So we found that, so we had to patch up this hole. So anyway, so it's really going from this barn, and then we built really nice offices and labs inside. We've recently built a clean room inside. But, you know, we've got carpeted offices and everything. So inside, it's a really nice building, and it's not too bad outside either. And of course, you can park there, which is easier than you can do in many places in Cambridge. So we moved into that facility in 2018. And our objective is to research and develop graphene devices and also other 2D devices. So we'll move on probably from graphene, but we're starting with graphene and focusing there. So just to emphasize the properties of our graphene, which we're calling next generation graphene: no metallic contamination, no transfer problems, uniform large area layers, 100% substrate coverage. We can dope the graphene and tune its properties while we're growing by MOCVD. It's suitable for high volume production. We believe it's suitable for photonic electronic devices and sensors. And the first product which we made is a graphene Hall effect sensor. So many people will know the Hall effect from the university days, but this is just a quick description of it. If you have a piece of material, a sensor, and it can be many different materials. It can be a semiconductor, it can be a metal, it can be graphene, and the Hall effect works in these materials. If you have a magnetic field B passing vertically through the material, as shown in the diagram, and you apply a voltage at right angles to the magnetic field, and we called V in, that's an input voltage, that induces a current to flow through the material perpendicular to B. The magnetic field exerts what's called a Lorentz force on the electrons, and it deflects them to one side. Again, it deflects them in a direction perpendicular to the field and to the current. And if there's what are called holes there, it deflects them to the other side. And that sets up what's called a Hall voltage that you can measure. So if you measure the Hall voltage, you know what the input voltage is, you can determine what B is, because there's a very simple equation that links B to the Hall voltage and to the input voltage. So you can use this to measure and detect magnetic fields. How are Hall sensors used? Well, they're used for measuring magnetic fields, but they're also used for measuring currents in wires. So if you have a wire or a cable carrying an electric current, then a magnetic field is generated around that current, that cable, and you can use the Hall effect sensor to measure the magnetic field and therefore to determine what the current in the wire is. It's a non-contact way of measuring currents in wires. So let's look at the performance of the graphene sensor. So does this graphene sensor really live up to its reputation of being a wonder material? So these are sensitivities of Hall sensors, different Hall sensors at room temperature, and the unit that sensitivity is measured in is volts per amp Tesla. A silicon Hall sensor has a typical sensitivity of 70 volts per amp Tesla. Compound semiconductor, so this is a quantum well of gallium arsenide, that's 850, significantly better than silicon. The Bosch graphene flakes that they were talking about in the press release, that was 1,250 if you look at their paper, but it's not manufacturable. The Paragraf Hall sensor is greater than 2000. So it's 30 times better than a silicon Hall sensor. But not only that, it will operate down at cryogenic temperatures. So the minimum temperature we found is about 100 millikelvin. That's the lowest we've got. We believe it will, as low as you can get, as you approach absolute zero, we believe our graphene Hall sensor will still be working. Not only that, it works better than at room temperature. So at these very low temperatures, the sensitivity is twice that at room temperature, 4,000 rather than 2,000. And Hall sensors like silicon, they don't work at cryogenic temperatures. The minimum temperature for Hall sensors to work is about 230 Kelvin. So it can do new things, not only do some things better than silicon, it actually is a cryo sensor, which other Hall sensors like silicon are not. Maximum Hall temperature operation about 500 K, and that's not limited by the sensor itself, not by the graphene, it's limited by the packaging on the material. And so if you can improve the packaging, you can improve this maximum temperature. Very radiation resistance, has a very high magnetic field range from -14 Tesla right through to +14 Tesla. And that's the highest that we've measured so far. So we believe again, if you have a stronger magnet, and there are not many around more strong than 14 Tesla, we believe it will work in that field. But when we're going to use a magnet which is 22 Tesla for quite shortly to test this out. But other magnetic sensors typically only work up to about 1 Tesla. So again, it's a sort of game-changing performance. And it also has very low power consumption. And it operates in harsh environments. So it's a package, as we said, graphene flakes are a unique package. If you get larger area graphene, then that also has remarkable properties. So this is the planar Hall effect, which I'd not heard of. We have a collaboration with CERN, and this was discovered while we were working with CERN on our Paragraf Hall sensor. And the planar Hall effect is because if you have a normal Hall sensor, which has a finite thickness, then you get spurious signals from magnetic fields which are not orthogonal to the sensor. So, that reduces the accuracy. Graphene is the thinnest material in the world. It's just 1 atom thick carbon atoms, and the planar Hall effect is negligible. And full characterization by CERN confirms the magnitude of the planar Hall effect is better than 10 to the -5 Tesla in a 1 Tesla field. So an order of magnitude better than any other Hall sensor. So this is an overview of the properties that I've been talking about. Very high sensitivity, greater than 2000 volts per amp Tesla, very wide operating magnetic field range, very wide temperature operation window. It operates at DC and also up to 100 megahertz. High voltage capability up to 2000 volts, very low power consumption, picowatts, no planar Hall effects. And the resolution is in parts per billion. The resolution of measuring the magnetic field is in parts per billion. And on the right, you can see a packaged Hall sensor on a test assembly. So this is now, we've been comparing our Hall sensor with other Hall sensors. This is a comparison of not only our Hall sensor with other Hall sensors, but also with flux gates and with nuclear magnetic resonance machines, which are the other ways you can measure magnetic fields. And if you look at the top line here, typical silicon Hall sensors are used in cars, have a maximum resolution in a 1 Tesla field, about 100 parts per million. The gallium arsenide-based Hall sensors, 10 parts per million. There's also a specialist Hall sensor, which is actually worse in resolution. Flux gates are very high. NMR pros are very high. Now on my screen, I actually can't see the final column because my image and other people's names are actually overloading. But I think from memory, our Hall sensor has a maximum resolution of 200 parts per billion. So you're actually comparing parts per billion resolution with parts per million resolution for Hall sensors, but the flux gate and the NMR probe are better. And I should add at present, because I'm sure we haven't yet optimized our Hall sensor. And I'm sure as we continue research on that, we can reduce we can improve the maximum resolution. Then if we look at the specified field range, a silicon Hall sensor plus or minus 0.5 Tesla, gallium arsenide 0.5, the bismuth one is better. Fluxgate has a very limited range of magnetic field, NMR probe 0.3 Tesla. And as I said, the graphene Hall sensor is so far plus or minus 14 Tesla, so much greater than any of these others. Planar Hall effect, negligible in the graphene. Minimum power dissipation, sorry, it's milliwatts for silicon, gallium arsenide, and bismuth Hall sensors. It's megawatts for Fluxgate and megawatts for NMR probes, and it's I think picowatts, which I can't see, but from memory it's picowatts for our graphene Hall sensor. So, and that's really important. If you're using a Hall sensor in a satellite, for example, then power consumption is really important. So very, very energy efficient. Upper temperature, the graphene Hall sensor is better than any of them. Cryogenic use, the graphene Hall sensor is then extremely good. Gradient field measurements, again, very good. Size and weight, I should say the Fluxgate and the NMR are both large objects. I mean, you wouldn't put an NMR machine on a tiny swarm satellite, for example. The graphene Hall sensor at the moment is 9 by 9 by 3 millimeters. And we're working on reducing the size of that at the moment, so to make it even smaller. So if you look at the overall performance of the graphene sensor, it's much better than any other Hall sensors. And it challenges Fluxgate and NMR in most of the boxes there. It's a resolution that the Fluxgate and NMR probes are better at the moment than the graphene Hall sensor, but in everything else, I think they're not as good. So this is now a few applications. I'm coming towards the end of the talk. So we're looking at a variety of applications, but this is one of them. We've got a partnership with CERN. And as I say, it's not only the only Hall sensor which has no planar Hall effect, it's the only Hall sensor that operates at cryogenic temperatures. And CERN are looking to upgrade their Large Hadron Collider. And they have this magnetic ring in Geneva, which is 27 kilometers long, and it's superconducting magnets operating at liquid helium temperature. So our Hall sensor, I think, is the only Hall sensor which will actually work in that. And they want to map the magnetic field in detail all around this magnetic ring. And they're looking, in fact, to put 10,000 Hall sensors all around this superconducting magnetic ring. So they're currently evaluating our Hall sensors and very pleased with the results so far. So that's one potential use of our Hall sensors. We've also got a collaboration with one of the leading aero engine manufacturers in the world. You can probably guess what it is. And they're interested in using our Hall sensors in their electric motors in their next generation all-electric engines for aircraft. And then now this is a sensor application. We're collaborating with a small sensor company. And why our sensors are important are because they're small, they're light, they're sensitive, they're low power consumption, they operate over a wide temperature range. So when you have a satellite going around the Earth, sometimes it's very hot when it's directly in the light of the sun, and sometimes when it's in the Earth's shadow, it's really quite cold. And our sensors, our graphene sensors, can cope with that. And one of the applications we hope to do is to map variations in the Earth's magnetic field from space. And we hope it will be sensitive enough to do that. And also to avoid collisions with other satellites is actually quite important. And then the final application I'll show, Paragraf, we're working with a major manufacturer of batteries for electric cars, because what we can do, we can have an individual cell in a battery, and we can put small Hall sensors on the top of this cell and have an array of small sensors, and we can measure tiny changes in magnetic field due to hotspots. So when the sensors, when the battery is being charged, then current flows into it. When the battery is being discharged, then current flows out of it. And so magnetic fields are generated in both occasions. And if they're uniform, that's fine. But if you have hotspots due to defects, then you'll get a spike, you'll get a change in the magnetic field, increase or decrease. And this gives you early warning that that cell will fail. And you can then replace just an individual cell rather than replacing a complete battery, for example. But this is an early warning device for failure of batteries in electric cars. And we believe we can do the same mapping of magnetic fields in field cells, and again detect potential problems in field cells. So this is just some of the examples of the use of graphene Hall sensors. Now this is the final slide apart from the conclusions. This is recent work, and organic LEDs, and they're used in smartphone displays a lot, and in the best quality TVs have organic LEDs, and they usually have indium tin oxide as a transparent conducting electrode in OLED displays. Indium is on the European critical materials list, and 50% comes from one country, which is never a good idea, and that country is China. And the EU states that iridium has an irreplaceable role in industry and society. So there's an urgent need to replace indium tin oxide. And I'm the Queen Mary PI on an Innovate UK exploratory grant to try and replace ITO with graphene. And one of my postdocs, Zicho Wang, has made an ITO OLED at Queen Mary. So this work has been done at Queen Mary, and he's made a graphene OLED identical under identical conditions, and using Paragraf graphene. Both emit bright green light, but the graphene OLED has a higher efficiency than the ITO OLED. So this is very suggestive that there's a real possibility that graphene could replace ITO in optoelectronic devices. And this would be a major breakthrough because people have been trying to do this for many years, and ITO is such a good material, it's been very difficult to replace. So this really is the final slide now. So the conclusions. So gallium nitride on large area silicon wafers are revolutionizing lighting and electronics. Paragraf have pioneered a new way that's using MOCVD, metal organic chemical vapor deposition, to make low cost, oh, this is on a special timer, to make low cost, high quality, large area graphene. Our graphene Hall sensor is the best performing Hall sensor in the world, and it's manufacturable. Our graphene OLED has a higher efficiency than an ITO OLED. Our MOCVD grown devices, they raise the expectations of what's been achieved so far, raise expectations that graphene biosensors and transistors may be manufacturable and be transformative if they are. Thank you very much.
Colin, thank you. That was absolutely fantastic. I don't think anyone has ever taken us from LED lighting that we might have in our homes up to satellites before.
Right.
And that the range of application is absolutely fantastic. And it just shows that how basic research then needs an awful lot of careful and skilled research in order to make it applicable in the real world. So thank you very, very much. I'll just remind our audience how to ask questions. If you're feeling brave, you can put up your virtual hand and ask a question by turning on your video. If you're feeling less brave, you can type a question into the question and answer box, not the chat, please. Then I only have one thing to look at, and I'll do my best to read out your question as carefully and faithfully as I can. And we have one question from John Grieve, who asks, what does a Hall sensor cost and how long is its working life?
Right, that's a really good question. So Hall sensors are, silicon Hall sensors are inexpensive, right? So the average motor car has between 20 and 50 silicon Hall sensors in, and the cost is really very low. I mean, I'm not sure what it is, but it's probably less than £1. With our Hall sensor, so at the moment, we're not trying to go for that mass market. So our Hall sensor is so good that it can do things that other Hall sensors can't do. And so we're trying to address the top end market And I'm not going to give you a cost because this is not a commercial talk, so and I may get it wrong. But how do you do the cost? So if we cost in all the development work that's been done, then you can see the cost is rather high. But no, so this is certainly more, at the moment, this will be more expensive than a silicon Hall sensor because it does have these remarkable properties. And I think if you're interested in the cost, then if you contact Paragraf, then the commercial people there will be very pleased to give you a cost.
Very careful answer. Thank you.
Right.
I think John Cook again has a question. And as he's been working hard to run this evening, I'm going to let him come in. Colin, can I just suggest you take your slides down so that we can...
now,
we've got a blank slide up at the moment.
Sorry, right. Oh, that's, yeah,
yep.
Much better. Thank you. Right. Thanks so much, Valerie.
Thanks for a fantastic talk, Colin. As you know, I used to be a material scientist, and it's great to hear about lattice mismatches and dislocation combination and all these things. You mentioned towards the end about the critical nature of the supply of indium, and we've heard lots recently about other critical elements. How does gallium stack up? Are we going to have a gallium crisis in a few years' time, do you think?
Right, so it's a very, very good question. Thank you. So indium is scarcer than gallium. Gallium is a byproduct of aluminium mining. So I think when bauxite, I think, is a mineral aluminium is refined from, you always get gallium, and it used to be thrown away because there wasn't a use for it. Oh. But now, but now there's not much of a use. Now with gallium nitride LEDs, there's a clear use for it. At the moment, it isn't a problem. So I think the reserves are quite good. So indium's much more, and in fact, in LEDs, invisible LEDs, indium is used there, but to a small extent. So the light emitting part of gallium nitride itself emits in the near ultraviolet. If you pass a current through gallium nitride, it will emit in the near ultraviolet. So it has a band gap. I don't want to become too technical for the audience, but it has a band gap which corresponds to the near ultraviolet, 3.4 eV. If you want to make visible light, then you add indium to the gallium nitride to get indium gallium nitride, and that has a smaller band gap. And if you add 10% indium, you get blue light. You get 15% indium, you get green light. So all LEDs have indium in, so that there's a potential problem for the future.
Okay, thank you.
I think we've got another John. We've got John Scott, who will be coming in as a video question, hopefully. John, are you there?
I think so.
We can,
video.
we can hear you. Yeah, there you go.
Oh, that's good. Yes.
Yes. Thank you for a fascinating talk. One thing that did cross my mind is that it's often said that development of novel things like this can be very difficult in the UK because of the availability of funding. Has that been an issue for you? And if funding were more readily available, would progress have been quicker, or do you think that hasn't limited what you've done?
No, that is a very good and important question. We were held up initially with getting funds, and in fact, the university has a fund, Cambridge University, and initially they wouldn't invest in us because they said they'd invest in other graphene companies which hadn't gone anywhere, and so they, wouldn't invest in us. And but then we did get, I probably shouldn't mention the names, but we did get a well-known venture capitalist invested in us. And when that person invested, or that company, then other ones wanted to. In fact, when they invested, Cambridge Enterprise phoned up and said, "We want to invest," and they actually led that investment round as well. Then, but the key thing we found was to get the first investor, and I shouldn't say venture capitalists are like sheep because that's very rude, but I mean there's a certain herd element, and if the first investor is well known for being a careful investor, then you get other people. So and in fact, we struggled initially, and we wanted to get, it's an interesting story, we wanted to get 1.5 million pounds seed funding because we wanted to buy equipment, and we actually got offered 2.9 million in the end. And we said stop. And so the Cambridge Enterprise said it was rather remarkable that this had happened. And then we went for what's called Series A funding. And I think we got 16 million Series A funding. And the initial investors continued to invest, which was important. And now we're going for more, we're just starting a funding round again for what's called Series B funding, where we'll have to bring in other funders. What is sad in a way is that the obvious place to go for funding is America. Yeah. And we've also, I mean, I don't want to take too long, but I think it's a very important question. I should say we have China, we're very, very keen to invest in us, and but we'd have to manufacture in China. And we just, just uncertain about that. But also America, we're told if we get a big American investor, they'll want us to move to America. And so the UK really has to try and sort this out, because, successful companies will not stay in this country. And it's a very important question that you raise.
Thank you.
Thank you, John. We have another question from John, this time John Staffel, who asks, what are other promising 2D materials?
Right, John. So we haven't investigated them yet. There's a number. There's molybdenum disulfide, for example, is looking promising. There's I think there's, you can have germanium as a 2D material. I think you have phosphorus as a 2D material. I haven't looked into these in detail. They all have different properties. I mean, what's remarkable about 2D materials is that the physics of them is very different from the physics of those materials in the bulk. So they behave usually very differently in the physics. And so until you investigate these other 2D materials, you can't deduce their properties from their bulk material, from their bulk properties. But other people, a lot of people in Cambridge are investigating other 2D materials and finding, again, on a small scale, they have remarkable properties. And again, I think the problem, again, is to scale up. So that's, for the exploitation, scaling up is what's really of key importance. And again, that's where often the funding is not easy in the UK.
Thank you. Another one from John Grieve again. How long is a graphene Hall sensor's working life?
Oh, yes, sorry, I forgot that part of the question. Yes. That is a very good question. I am not sure what limits the lifetime. I know, I'm just thinking, if you think of what's the limiting life of a gallium nitride LED, then I can give you the answer to that, but it may be relevant to graphene. So a gallium nitride LED, a light bulb that you have, the actual light bulb, if you buy in a shop, and it's a good quality one, it will last for something like 25,000 hours. And what limits that is actually not the lifetime of the gallium nitride chip, it's the lifetime of the control electronics, because no one's wanted domestic electronics to last that long before. It says 25,000 hours is 11 years continuously, I think, or something like that. The gallium nitride chip is believed to last 100,000 hours. What eventually probably limits that is interdiffusion. So slowly, you have an indium gallium nitride quantum well emitting the light, and you've got gallium nitride on each side. You've got some aluminium nitride there as well. And these are slowly diffusing these atoms, especially as the light bulb's operated, maybe in a hottest temperature. So that's what I think limits the lifetime there. With I should have said, our Hall sensor is gallium nitride on a sapphire substrate. We just deposit directly. And the bonding is essentially van der Waals bonding between the graphene and the sapphire. And so I don't think there's interdiffusion there. If there is, it's negligible. So I would expect to have a very long lifetime. It might be that the contacts diffuse with the graphene, but it's a really good question. So, and they haven't been around long enough to test. This is another, another problem. So I remember when we were doing gallium nitride LEDs, one member of our teams called Ted Thrush, he had the gallium nitride LEDs we made on his garage at home. And you know, the first LEDs we made were in about the year 2000, and they were still going, you know, 20 years later, as it were. And so yeah, you need to be able to keep them for some time to see what the real lifetime is. But I would expect them to have a good lifetime.
That's good.
Prince Philip, yes.
That's fantastic. I think the UK is going more towards wanting things to last and be repairable than
Yes.
simply going and buying another one. Someone is hoping you can apply your research elsewhere. Peter Clark has asked, can your equipment be used in the search for nuclear fusion?
Oh, this is a really good question. Yes. I had a slide which I took out, so I thought the talk would be too long. We're part of a grant proposal of a multi-nation nuclear fusion experiment, and I think we are talking to tokamak people at the moment. So yes, they have a lot of Hall sensors because they operate with, you know, very high magnetic fields and very high temperatures, and we believe our graphene sensor can really be used for nuclear fusion. So thank you very much.
That is looking brilliant. I'm keeping a careful eye on the time, and I think perhaps if there are no other quick questions, we should wrap up here. I think, Colin, you've given us you deserve the prize for the most widely applicable talk. If you've gone from traffic lights to satellites to home lighting and then on to nuclear fusion, that's absolutely impressive. Thank you ever so much for a fantastic talk. I'll remind our listeners that we're back on the 10th of May with Professor Cecilia McCosco, who's talking about wearable and mobile sensing for health diagnostics. I'm looking at John and I'm wondering if he has one final question.
No. No, I just wanted to say thank you. Excellent talk and very good talk from Jenna as well. Both very good talks. Thank you so much.
Well, thank you very much. It's a great pleasure.
Brilliant.
Yeah,
Thank you
for having
everyone.
us.
And we'll hopefully see you all on the 10th of May. Thanks and good night.
Good night, everyone.
Good night. Good night.